Okay, folks. So, last time we've been talking about discrete-time Fourier transforms for a while now. We're actually getting close to the end, believe it or not. And last few times we've been looking at how do you actually derive or compute the discrete-time Fourier transform. And the context that I gave you was, well, this frequency response thing, which is a discrete-time Fourier transform, is a really important thing, really helpful. Well, today we're going to finish off the description of how we can do the computation of it, including a shortcut way that takes advantage of some of the properties, and then start talking about if it's so useful, prove it to me. What's it good for? How do we use the discrete-time Fourier transform? So finally we get to doing in the learn by doing part. Okay. So, but just to recap where we were last time, we were getting quite excited about the convolution property. That told us that we can do system analysis in the time domain. We can compute the output signal for a system by taking the input signal and convolving it with the unit sample response. And then we said, well, this transform thing is kind of nice because it has this convolution property, or tells me how I can transform the operation of convolution into something simpler. If I take the discrete-time Fourier transform of my input signal, I get my x of f. If I take the discrete-time Fourier transform of the unit sample response, I get h of f, the thing we're calling the frequency response. And if I want to know what the discrete-time Fourier transform of the output signal is, well, I've got to take this convolution process and run it through the transform as well. And it turns out when we take convolution through that as an operation through the discrete-time Fourier transform, the equivalent of that in the frequency domain is multiplication. So if I need to do a convolution, I can choose to do it on time signals, or I can do it by multiplication of their frequency spectra. And that's probably going to be easier. And so this will become our preferred way, or one of our preferred ways to do system analysis, is to do it here in the transform domain, where it's simply multiplication. And that's really only good, though, if this process, going from time domain to frequency domain, is easy. Well, that's why we spent so much time looking at, well, turning it into a lookup problem, or a lookup and manipulate with some properties problem. This multiplication, it's not hard. It's algebraic. If I've got analytical expressions, it's graphical if I've got graphs. I've still got to do the inverse transform piece. Well, that's going to be the backward version of what I did to come into the domain. So I'm going to have all the same sorts of options for that. And we'll talk about that today. But again, this has to be easy for me to do if I'm going to want to use this as my system analysis method. If it is, then we've got a way to do convolution without having to do convolution. And a bonus, this thing that links my input and the output, this thing we call the frequency response, that has its own significance, its own usefulness, and it happens to be nothing more than the discrete-time Fourier transform of the unit sample response. So all these things are linked together. And now the thing we didn't get to talk about last time is this process really is still not looking so good. Back up to this picture. I like this. I like this multiplying instead of convolving. No good if this is hard to find. Well, what is that? That's the discrete-time Fourier transform of the unit sample response. How do I find the unit sample response? How do I do that? If I have a difference equation, how do I find the unit sample response?
Plug in an impulse for y of n.
Plug in impulse for y of n, and whatever comes out is, by definition, h of n. It works great for FIR filters. If I have an IIR filter, what do? I'm going to solve a difference equation. You know, make my head hurt. That was midterm 1 stuff. Here, maybe solve a difference equation. If I'm going to solve a difference equation, I'll just solve it for the real thing and just go home. You know, So this, even this nice new method that lets me not do convolution isn't helpful unless I have an easy way to find h of f. And the answer is, of course, there is an easy way. There's a question first.
Yeah, so for finding the inverse DTFT of
Mhm.
y of f, is that just a lookup table or is there an equation for that?
Yes to both.
Okay.
So the same lookup table I used to go from here to here,
Yeah.
I can just work backward, use the same table.
Yeah.
So typically that's what we're going to want to do.
Yeah.
But there's also a defining equation, and we'll look at that. But we're going to mostly want to use the lookup table when we can. Okay. All right. So what's the good news? The good news is I can find the unit sample response and the discrete time Fourier transform of it, the frequency response, directly from the difference equation in a easier method than solving the difference equation. Now that I have these transforms, here's how it works. We're going to use the convolution property and the time shift property. Those two together are going to be my key. And you did this in 228 with differential equations using the derivative property and transforms and convolution property. This is the equivalent to that in discrete time systems. So we know the frequency response is the discrete time Fourier transform of the unit sample response. And if the transform of x of n is x of f, we also know that the transform of y of n is y of f, and the convolution property says that I can get y of f from x of f and h of f by multiplying them. Okay. If I can do that, I can rearrange this to say, how do I get h of f? Well, it's nothing more than the ratio of y of f over x of f, the ratio of the discrete time Fourier transform of the output signal and the discrete time Fourier transform of the input signal. And so, so if you give me those two pieces, give me an analytical expression for y of f, give me an expression for x of f, I take the complex ratios, I've got h of f. And now I just started you down a circular path. To find y of f, I need x of f and h of f. To find h of f, I need y of f and x of f. Give me two, I can get the third, but I need two. All right? So far that doesn't look real helpful. Well, the difference equation is what makes it all worthwhile. Because the difference equation tells me how do I connect x of n to y of n. So it could potentially tell me how to connect x of f to y of f if I take the discrete time Fourier transform of the entire difference equation. So here's a generalized difference equation. I'm going to take the DTFT of every one of those terms. And because the DTFT is a linear operation, I can, if I want the discrete time Fourier transform of the sum, I take the transform of this, add it to the transform of that, add it to the transform of that, and so on, so on, so on. Discrete time Fourier transform of y of n is y of f. That's easy. Discrete time Fourier transform of a times y of n is a times y of f, right? Linearity. Discrete time Fourier transform of a1 times y of n minus 1, no, that's a1 times y of n. Sounds like it's going to be a1 times y, capital Y of f, and that's a sample shift. We know how to do sample shifts. Shift property says just multiply by e to the minus j 2 pi f times the amount that I shift, that I delay. So this transforms to a1 e to the minus j 2 pi times 1, and that one sample shift f times the Fourier transform of y of f. Similarly, this term would transform to a2 y of f times e to the minus j 2 pi 2 times f. And so on and so on, for however many terms are on the right, on the left-hand side. right-hand side, B0 times x of n transforms to B0 times capital X of f. B1 x of n minus 1 is B1 x of f times e to the minus j2 pi 1f, and so on and so on and so on. So transforming the difference equation with the shift property is trivial. Now, factor out y of f on one side, factor out x of f from all the terms on the right side, and h of f is the ratio of y of f over x of f. So take y of f divided by x of f, which leaves this term divided by this term. And so every frequency response is going to have potentially this sort of, well, definitely have this sort of form of a frequency response, because it starts with a linear constant coefficient difference equation. The numerator is always going to be E0 plus B1 e to the minus j2 pi f plus B2 e to the minus j4 pi f, and blah, 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 blah. And 1 plus A1 e to the minus j2 pi f, A2 e to the minus j4 pi f, and on and on and on and on. So it's, you could go through those steps algebraically every time, or just know it comes into that form. But we can go directly from the difference equation to an expression, a complex ratio that is the frequency response, without needing h of n first. There's our shortcut. That's what's going to make this easy for me. So I give you a difference equation, you got h of f. It's algebra. Isn't that nice? I know it's 420, but that's exciting stuff. Come on. All right. Let's do it. Let's see how easy this is. Take our recursive filter. Oh, we've just beat this thing to death. We've done this every which way, but now, the easy way. Here's the difference equation. Let's transform the difference equation. Y of n becomes y of f. Minus alpha e to y to n minus 1 is minus alpha e to minus j 2 pi f times y of f. X of n is x of f. You're done. Make the ratio y of f over x of f. Well, factor out the y of f's first. Then make the ratio y of f over x of f. It's simply 1 over 1 minus alpha e to the minus j 2 pi f, which, if you look back in your notes, we derive 4 other different ways. I like this way. That was pretty easy. Okay? And, you know, more complicated, longer difference equations just mean you're going to get more terms in here. Yeah?
So is this really anything special to say that the transfer function equals the output over the input? Isn't that kind of something we already knew?
We knew that. All you're saying is not as exciting as I'm making it out to be.
I guess it's like cool that it's in the frequency domain as well as like the daily domain.
Yes, it's cool. This is in the frequency domain. Yes, well that's, but no, nothing new. This is the same thing with the continuous time Fourier transform. We did it with differential equations, and we used the derivative property. Same trick. But I contend it's just as cool here as it was there. And actually, this is the coolest form. Because it's got frequency in it. It's got physical stuff in it. If I know what frequency is, and I can get a frequency response, and I can use that, I can think of what that's going to do to my audio signal, or that's going to do to my RF signal, or my radio signal, or my photons. But it'll be easier. This same thing will do the same thing when we get to Z-transform land, just like we did the same thing in Laplace. And it'll be all the same mechanics, except it's going to look prettier because instead of e to the minus j, well, e to the j anything, it's going to be z's. And it's going to look easier. It's going to be much less scary. Less informative, but easier. Well, I shouldn't say less informative. It's actually more useful, but not quite as physical. This has physical stuff, frequency in it. So I like this one. Okay, questions on the method? All right. We've done this before, we've hinted around it, we've assumed you've known this, but I'm going to do it one more time. I apologize for those of you that this is the 3,000th time you've done this. Some people, it takes a couple more times, and I really, 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 really want you to know, understand this. If I give you a complex ratio meaning a function that's potentially a ratio of two different functions complex functions of a particular variable. How do we turn that into analytical expressions for the magnitude and phase? Well, this one's a little bit easier, but the because I have an actual real value in the numerator, but we'll treat it like it was imaginary and just go through the mechanics so that we're comfortable with how you do these things. Why do we want to do this? Well, I give you a complex h of f. I don't know how to interpret that. I give you a function of what the magnitude versus frequency that's a real valued function. Well, that's something I can plot in Excel. Right? Same thing for a phase response. I can plot that and get some information out of it. So how do we go from this complex exponential mess to something that's usable and I can wrap my mind around and draw figures for? Okay. If you have a complex ratio, a ratio of two complex functions, we want the magnitude, we want the phase. Well, the magnitude, we would need the magnitude of the numerator divided by the magnitude of the denominator, right? That's how we deal with complex ratios. Magnitude of the numerator, well, it's a real value function, so it's 1. That's easy. Denominator, I do have a complex function there. You can't play any funny, the coefficients are different, so I can't do any funny Euler identity thing. Well, I can't pull out a phase. So, but I can use the Euler identities to convert this exponential to a cosine minus j sine function, and then find the magnitude of that complex expression. Well, that's I've got to break it up into real parts, and both the 1 and the minus 1/2 are real. The minus sign is the imaginary, minus plus for the sine term there. And the magnitude is square root of the sum of the squares of the real part and the imaginary part squared. And it turns out this one, you have to actually FOIL out this square here, this polynomial, gives you a 1 squared minus double the product of the roots, and plus this squared, 1/4 cosine squared, 1/2 sine squared, or 1/2 sine quantity squared becomes 1/4 sine squared. And we have the cosine squared plus sine squared, both the same coefficients, so they can be combined into 1. So I have 1 times 1/4 added to 1 gives me 5/4, and the square root of that would be now a real value function, no more j's. And I could literally plot this versus values of f in a frequency response, magnitude response plot with Excel or any other plotting tool or any other plotting calculator. For phase, well, if I have a complex ratio, the phase of the quotient is the angle of the numerator, the phase angle of the numerator minus the angle of the denominator. What's the angle of 1? 0. It's a real function, it's positive. So real and positive has no phase. Negative would be minus 180 degrees, or plus or minus 180 degrees, negative for negative sign. So that's easy. And I'm going to subtract off the phase of this quantity. And again, that's a complex value that I'll break up into real and imaginary parts. And I can't do any better in this case than an inverse tangent. Inverse tangent of the imaginary part over the real part. Here's the imaginary part. Here's the real part. And so that's the phase of the denominator piece. The phase of the quotient is 0 minus that, which is where the minus sign comes from. Okay. So if you haven't been clear on that, if you've been wondering where we get some of these expressions from, that's the computations that we've been going through. Please be comfortable with that. All right. We can plot those, and there they are. You plot this function, magnitude function, versus capital F, we get this function. If we plot this inverse tangent, negative inverse tangent versus capital F frequency, we get this function. And notice they both are periodic, like they're supposed to be. They would keep repeating as I put in F equals 1,000,000, I'll still get a valid answer. It's just going to be a periodically repeating copy of these, with those graphs that we have up there. We only need to care about the principal range. As you give me that, you've told me the whole story. The rest are just copies, copies, copies. Same thing down here. And what would we say? Well, what good is this? Well, we can interpret this and say, well, what is that? It's not a linear phase thing. It's linear here. So for a range of frequencies, it's got a nice phase response, but outside that, it gets a little squirrely. Let's see. It boosts DC by a factor of 2, but attenuates anything above 0.2. It's multiplying it by something less than 1, so it's attenuating things, but not a whole lot. So it boosts some frequencies, it attenuates others. I still call it a filter. I wouldn't call it a very good low-pass filter, but it's a filter. But when I say I like the frequency response, there is a lot of information right there. It tells me what this discrete time system is going to do to a cosine signal of any frequency I put in. The information is there. Yeah.
Is it ever useful to put in like a Bode plot form?
Is it ever useful to put this in a Bode plot form? Turns out to be less helpful in discrete time because of that repeating the periodicity. Then you start compressing using the logarithm frequency axis, it gets looking squirrely. So we usually actually plot discrete time in a linear frequency axis. You could do dBs, that might be helpful, but to compress the dynamic range of the amplitude, but usually frequency is done linearly. Okay. So we've got this shortcut method. A nice way to get the frequency response directly from the difference equation. All right. Let's talk about some applications. Switch to some new slides here. Okay. What is this good for? Lots of stuff. We can use the DTFT to find the frequency content of our discrete time signals. If I take the DTFT of the x of n. If you give me the sample response and I find this DTFT, well, that gives me the frequency response. All that great information about what the system is going to do to any cosine I put into it. I can actually use it to give me a shortcut way to find my sample response. I can use it to find the steady state response of the system for any discrete time harmonic signal. That's what it's really good for. And as we saw with the convolution property, I can find zero state responses using the convolution property in these transforms without doing convolution. So we're going to go through all those, and we'll finish up on Monday. But let's see if we can attack those first 4 today. First one, you give me a signal, x of n. I take a DTFT, I got x of n. Okay. What does that mean? Well, here's the signal. Delta of n plus 1/2 delta of n plus 1 plus 1/2 delta n minus 1. A non-causal signal, okay. Got just 3 non-zero samples. And I want to know what's the frequency content of that signal. And actually it's almost a triangle, kind of, sort of. All right. What's the frequency content of that signal? Well, we just take the DTFT, and for a finite signal like this, I have just 3 sample values. Taking the DTFT is easy, right? Because impulses become constants, and delayed impulses become constants with e to the j somethings, right? So the delta transforms to a 1. The 1/2 delta of n plus 1 transforms to 1/2 times 1 times e to the plus j 2 pi f, shifting plus 1. And this one is 1/2 times e to the minus j 2 pi f because of the delta minus 1. And here I've got 1/2 e to the plus j something plus 1/2 e to the minus j something. That's a cosine. So this particular signal has an interesting frequency shape, frequency content in the principal range. It's a raised cosine function. Notice that it's real valued. Why is it real valued? X of f frequency of DTFT is usually complex. Why is it real? What makes it real? Yeah.
Maybe the phase is 0.
phase is 0, yeah, that's a true statement. But what about the time function? It's forcing it to end up with a real value x of f. Something about the symmetry. Who remembers the rules? I have a real value function, so that implies a certain symmetry here. That doesn't make it real. Something makes it real. I need a certain kind of symmetry. Even symmetry. My time function, if it's even symmetric around n equals 0, I will get a real value x of f. If I had taken this signal and say, I like that signal, it's not causal. Let me make it causal. Let me move it over by 1. Would this still be? No, it'd be complex. Can you tell me what it would be? How would I change this if I shifted that by 1? How would I change x of f? What happens to transforms when I delay the sample? Just not saying it loud enough. When I delay by a sample, what does it do to the transform?
It's the same.
Hmm?
It's the same.
The same? Magnitude's the same. Multiply by e minus j2 pi f. Thank you. I was getting right there. Yes, shift property. Multiply this whole thing by e minus j2 pi f. Makes it complex and doesn't change the magnitude. It just adds a phase to it all. Okay, thank you. Whew. All right. And so I would interpret this as saying, well, okay, my signal has more low frequencies than it has high frequencies. It's kind of a low pass sort of signal. Yeah, okay. If that thing that I transform is my unit sample response, though, what I get out is still a frequency spectrum, but it's a frequency response. It's the response of the system to different cosines of different frequencies. So we've looked at ad nauseum at two different, an FIR and an IIR filter. And the FIR filter had this kind of H of F, the IIR had this kind of one. And these are telling me what these two systems would do to different cosines of different frequencies or sines. So if I put in a DC, a constant value, this one says, well, I'm going to let that constant value through. I'm going to multiply it by 1 and shift it by 0. I'm going to do nothing with DC signal. This one says DC, oh, you give me a DC signal, I'm going to multiply it by 2, and I'm not going to shift it at all. If I put in a signal that's cosine 2 pi n times 22 cycles per sample, well, this particular filter is going to scale it by 0.8 and shift it down, shift its phase by about, I don't know, about 0.23-ish pi. Whereas this one at 0.2 is going to do nothing, multiply me by 1 and shift my phase by 0.18 pi maybe, something like that. So I can read off directly from this frequency response. What is this system going to do with a signal of any frequency, just by finding that frequency in the plot, see what it does to the magnitude, see what it does to the phase. That's the power of that frequency response chart. Okay. If I was foolish enough to take those two filters and put them back to back and ask the question, what's the frequency response of the two of them together? So we put them in cascade, we put them in series. What happens to the impulse response for two systems that are in series, that are cascaded? What's the impulse response, equivalent impulse response of the combination? How do we derive that? Convolution. So those convolve. We take that into the frequency domain, guess what? We would multiply H1 of F times H2 of F to get the overall frequency response of the combination. And so that's kind of powerful if when I have back-to-back systems, I can quickly determine the overall frequency response of the combination by multiplying the individual responses frequency by frequency. So for instance, we did use those particular two filters, our FIR filter followed by the IR filter. If I wanted to know what's the frequency response of the combination, I would multiply every value in this plot by the corresponding values in this plot. And for phase, I would add the values in this plot to the one below it. And you would get something like this, because that's when you multiply things in frequency that we need. We multiply their magnitudes when we add their phases. So hopefully visually you can convince yourself that's what's going on. So for example, when this one goes to 0, well, then the product should go to 0. This one, we have pretty much the same shape as the middle one, except this guy's tapering it down faster, so it's a little bit narrower. Over here in phase, we're essentially taking this phase response plot and adding a linear phase to it, tipping it up, and putting these phase jumps in as well. So we're combining these two to create the combination there. Yeah.
So since this is the same process as finding y of f using x of f and h of f, to find the phase of y of f, would it be the same process, just adding the phase of x of f?
Yes, if this was the frequency of, if this was the frequency spectrum of the input signal, and this was h of f for the system, you would multiply their magnitudes, add their phases, and have the magnitude and phase of the output. Exactly. Same thing. So that's another way to do it graphically. You can do that, or analytically with the actual functions. Everybody see that? Powerful stuff. Okay. So you give me h of n, I can find h of f, and oh, by the way, we just saw that you can actually take the difference equation and find h of f. You should be getting good at that by now. We took this example, right? We derived, transformed it, rearranged it, put it, if you want, y of f over x of f. This gave us a ratio of that over that. That's cool. But guess what? All that stuff is linear. All that stuff is invertible. And so I can run that process backwards. If somebody gives me a complex expression for the frequency response of the system and says, I don't know what that system was, but here's its frequency response, I could tell you what the system was. I could go backwards, right? And it's literally running this process in reverse, right? So flip it around. Start with your frequency response. Now cross multiply, right? Take your y of f, multiply by the denominator over here, take the numerator of that, multiply by x of f. Distribute through the y of f's and the x of f's. Inverse discrete Fourier transform each of those terms one at a time. And using the shift property, recognize this is a shift by one. And voila, difference equation pops out. So we can go both ways. We can go from difference equation to frequency response. We can go from frequency response backward to the difference equation. In fact, I'd like you to be able to do that. Let you finish your notes there. Everybody see what we did there? It's essentially, literally the process we did to go from difference equation to frequency response running backwards, undoing all the steps. Because h of f is y of f over x of f. And in fact, that's a game that's called system identification or deconvolution. If y of f equals x of f times h of f, if that's convolution, involving the input with the system to get the output, deconvolution is you tell me the signal that comes out of a system and the signal you put in to get it, and I could, on a good day, tell you what the system is. It's like somebody handed you a black box and said, I don't know what this does. And you put in a really smart test signal, and measured it, and measured what came out, and created that ratio of the frequency responses, you could infer what is the frequency response of the system. That's backwards convolution. Uh-oh. No, I don't want to change the color scheme. Stop asking. I don't know why it does that. Okay. All right. That said, the fact that I can go from difference equation to frequency response makes it probably the easier way to find the unit sample response of the system than solving the difference equation is. So you give me the differential difference equation, I could solve it with some special conditions and find h of n, or I could find h of f, inverse transform it and find h of n, and that's usually easier. As long as this isn't too bad, and here's the answer to your question, how do we do inverse transforms? Well, we can do the definition. We can plug in h of f into, oh, it's an integral inverse transform, not a summation, because f is a continuous variable, so we've got to integrate over all values of f, the frequency response. Oh, but it's periodic, so we're going to integrate over one cycle, which would be f equals minus 1/2 to plus 1/2, or 0 to 1, whichever one you prefer. And it's the thing with the same transform kernel we had for coming into the domain, but we're going back out with a plus sign. So h of f equals plus j 2 pi n capital F df. You could do that. Yeah.
Would it be the same process for finding x of n and y of n?
Would it be the same process? Yes, if you had when you have y of n, you have all the same options. You can use the integral form, or our favorite way, use the tables. Right? Look it up if you can, or modify it with the properties and then look it up. And if well, if that fails, well, if you have something that's not in the table and it has a lot of terms in the denominator, then partial fractions is going to be back, I'm afraid. We won't have time to do it today. Monday we'll do a system analysis that includes an inverse transform with partial fractions, because you got to play with the technique a little bit with discrete time systems. So we'll see how to do that, but we'll have a happier weekend knowing that we're not doing partial fractions over the weekend, at least. I'll say that next week. For example, this system, it took us a while to derive the sample response of this. We did it with a recursion table, and then we did it with solving the difference equation. Now that we have this shortcut, we know we can find h of f really quickly, and then inverse transforming that, well, that happens to be one that does actually inverse transform the table. We would find something that looks like it and say, voila, there's your transform, and so this must be the inverse transform, and we're done. And that's how you'd like it to go. Again, the problem is our little lookup table doesn't have a lot of entries, and certainly doesn't have anything with more than a second order term in the denominator. So if I have a more complicated system, I'm going to end up doing some partial fractions. And particularly when we start multiplying x of f's by h of f's, we're going to get higher order ratios that we're going to have to inverse transform, and we'll have no choice but use partial fractions. Okay. This really busy chart is just a way to say you now have at your disposal 1, 2, 3, 4 different ways to describe the dynamic behavior of a system. The difference equation is kind of where it all started. Tells us how the output is related to the input through a linear constant coefficient difference equation. We can represent that graphically with a block diagram. Now we've also derived an impulse or unit sample response, h of n, which we can use for system analysis for relaxed systems. It also has all the dynamic behavior of the system information built into it. And its transform similarly has everything we need to do system analysis. So we've got all these different ways to describe how is the system going to behave to capture that information. And if you give me any one, I can derive the others. Right? If you give me the difference equation, we've got an easy way to find the frequency response. If you give me a block diagram, I can recover the difference equation from it and vice versa. And we said, if you've got the difference equation and you want the impulse response, well, I could jump directly to it by solving the difference equation, or I can jump over here and jump back with transforms and inverse transforms, whatever way is going to be easiest. My message to you is you need to be able to do all those jumps. You need to be able to go from here to there, from here to there, 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 whatever it takes. You need to be able to, I give you one of those, you should be able to get 80 of those. So please make sure you're clear on how to convert one to the other. That's an important skill. Okay. The big application, the big kahuna, the main reason that we like frequency response, the reason I said this is the best kind of function, is for exactly this job. It is all the information that I need to tell you what is the steady state response or the forced response of a system to a harmonic signal. Harmonic signal being a sine wave, a cosine wave, or any combination of sines and cosines with different frequencies. That's what it is. It's the frequency response. The response of the system to signals of different frequencies. So that plot, that function, is all the data I need to tell you exactly what the system is going to do to any sine or cosine of any frequency I happen to try. So if it's got one frequency, no problem. If it's got a lot of frequencies, no problem. All the information is there. If I need to know what's the system going to do to a signal of a particular frequency, well, I'll just plug in that particular frequency in h of f, get a complex value, evaluate its magnitude and phase, and that's the information that I needed. That's all the information that I needed. It's the response of the system to that harmonic input that contains that particular frequency. And by harmonic inputs, this is what I'm talking about. You have a cosine with some digital frequency f0, so it's a discrete time signal, so it's a 2 pi nf. Might have some phase, might have some amplitude. I put this signal in the system, I can tell you what comes out if you tell me what h of f is. At least the steady state response, the forced response. That's what this picture is telling you. Here's the magnitude, here's how much the system's going to scale up a signal of any frequency. Here's how much it's going to phase shift a signal of any frequency. So, and if I put in, for example, some a cosine 2 pi n times 0.2, well, this is frequency 0.2. You go over to your frequency 0.2, look up what's the magnitude for the phase at 0.2, look up what phase we get, and those answers are all the information that I need. So tell me the steady state response, meaning no transients. Somebody turned that cosine on a long time ago. We also have to assume the system is stable, or this doesn't work. Okay. So there's, notice in my function, my input is a cosine, there's no u of n here. This, somebody turned this on a long time ago. All right? If you put a u of n next to it, well, then there's going to be a transient at n equals 0. I'm not going to see that with this response. I got to do system analysis for that. But for steady state analysis, for forced response analysis, this is what this is good for. Okay. In 5.5 minutes, let's do an example. And if I put in a harmonic signal with some magnitude and phase and frequency into this system, what's going to come out is exactly the original signal, its original magnitude, its original phase. The only thing a linear time invariant system is allowed to do to it is scale it and shift it. How much it scales it is, I take this complex h of f function, plug in the frequency of my cosine, I get a complex value, take the magnitude of that, that's how much I scale it. Take the phase of it, that's how much I shift it. Voila. If it does an alias. If it aliases, what else changes in this output? The frequency changes too. That's not good. Okay, let's see if we can take two examples. One without aliasing, one with aliasing, to see how we deal with those two cases. Does everybody see what we're doing though? How we're using that frequency response. Numeric example might help. Okay. We'll use our simple recursive filter. We've got its h of f, we're ready to go. And let's put in this signal. 4 cosine 0.3 pi n plus pi over 4. That's the signal coming in here. I want to know what comes out that in the steady state. Let me turn this on a long time ago. Okay? What is the steady state output? What frequency is this signal? What digital frequency? 0.15 cycles per sample. So we take 0.15, then we find 0.15 digital frequency here on the magnitude response and the phase response. 0.15, 0.15. And on the magnitude response at 0.15, I read off about a magnitude of about 1.5. And for phase, it looks like it's about minus 0.15 times pi. So we find that value, we evaluate the magnitude and phase of those two at that particular frequency and get those values. If I didn't have the graph, I could literally plug in f equals 0.15, let's do that, into this expression, 0.15, and find out that actually, more exactly, the value is 1.506. And in this phase expression, we plug in f equals 0.15, and you get minus 1.46. So graphically or analytically, we get the same value. And that's all I need to know. Because what's going to come out, finish writing down there, is the original signal scaled by 1.5 and shifted by minus 0.15 pi. Right? So we take that original function, it was 4 cosine 0.3 pi n plus pi over 4. We scale its magnitude by the 1.5. We add a minus 0.15 times pi per phase, and scale these together, add the phases together, and get what comes out in the steady state is 6 cosine 0.3 pi n plus 1/10 pi.
Where was the alias test for that?
The aliasing test was the digital frequency was 0.15.
Yeah.
If it's below 0.5, the Nyquist frequency, it's not aliasing. Everybody okay with the mechanics? All right, see what we did there? We extracted the magnitude and phase at that particular frequency that we put in and used it to scale and shift the input. All right, what if it aliases? Well, let's take one of the aliases. All right, let's use here's my 3 sine 1.58 pi n. That's like a continuous time signal with an argument of 1580 pi t sampled at 1 kilohertz. So we divide this by 1,000 and we would have this digital frequency. The real digital frequency is half that, right? So 0.79, which is bigger than a half. So therefore, it will alias. Where's it going to alias to? What frequency will it end up being at?
Negative 0.2.
Minus 0.21. Subtract 1 off of here, we get minus 0.21. Right? Okay. Now, the $64,000 question. I know what frequency is coming out, but I need to evaluate h of f at the frequency of my signal. Which one do I use? Minus 0.21 or 0.78? Which one do I look up?
179.
Turns out it doesn't matter. Because it's periodic. If I'm over here and I go down by 1, I get the same answer. So take your choice, doesn't matter. Here's the punchline. Let's get the values. Let's get some values here. The magnitude of 0.79 turns out to be 1. The phase turns out to be 0.16 pi, which you can get either by plugging in 0.79 or minus 0.29 into the magnitude of phase functions. We want to get to the same answer because it's periodic. And so what comes out is scaled by 1 shifted by 0.16, but remember, we gotta put the alias frequency in. Don't miss that part. And if it's a negative frequency, we gotta make it positive by readjusting it to taking the negative of the argument and a minus sign out in front if it's a sign. So that's what happens with aliases. Same method. The frequency response is very forgiving. It's a periodic function. But we do have to remember, just as we did when we were doing sampling theory, that the signal coming out is going to be a very different frequency than the signal going in. Again, those of you who have me for 368 learned that this week, right? In lab. We're seeing aliasing all over the place. All right, we'll pause there. We'll pick up on Monday, do some real system analysis, zero state response stuff, and maybe we finish up DTFT. Yes. Have a good weekend.
Yes. Nice of you. Do you actually use that?
It sounds like you It's okay. Yeah, you are. Oh!